All right, so basically the encoding, the feature map or encoding is translating the quantum data, the classical data to quantum data, right? And there are so many different methods, all right? There are so many different methods, you can search them. And then you have variation in quantum circuit, which is depending on your design. Basically, you're applying the gates that we explained and Amna explained, the X rotation, the Y rotation, the C naught, and the other rate in certain order, depending on your design. Then you're measuring, because what would it be without measuring? And then you give it to the cost function, right? The cost function could be, honestly, any optimization function that also depends on you. Again, it's really nice because even when I do my research, I try and know a lot of stuff. So if something works with you necessarily, it might not work with me. That's because your data could have a nonlinear relationship that's different from mine, right? So once that cost function, optimizes it, just gives it back again in here, update the parameters and repeat, all right? Do we need to every time encode the feature? I don't think so. We just need to do it once. And now I lost the clicker. Sorry. Oh, there it is. Okay. So having stated that, let's look at quantum neural networks, okay? So we already explained what neural networks are. I'm trying not to really get in details. I know you guys are really almost bored when I go home. So now, when we explained, now I explained deep learning, and I'm not basically explained VQC. Don't you think they have similarities, right? Don't they both want to, decrease the loss, find the best theta that, not exists, but the best theta that serves your problem? So basically, it's almost the same. Here, we train to minimize loss function. Both concepts, we perform function approximation. And these are the main differences. So look, in the classical neural network, we have nonlinear activation function, right, that introduce nonlinearity. But in the quantum neural network, we have entanglement operations. We have in the classical irreversible operation, but the quantum is reversible unitary operation. By the way, I think I forgot to mention those unitary operations are reversible. And then you have classical feature space because you need to put, even in classical, not classical, I'm not going to use the word classic again. In the original AI computing, we do most, depends on the algorithm, we do translate our data into feature space. Here you have the Hilbert space representation, which is the quantum. And remember the classical weights I was explaining, the weights and biases in normal neural network that learns over time. And here it's parameterized quantum gates, okay? All right, let's look at the, again, I know you are bored of mathematical symbols, so I'll go really, really quick. Let's go look into the architecture and how it's represented in math. So we start, again, by classical input data, and we apply, depending on how many qubits we have, we apply the initial state to the feature map. Again, we need to embed it into high dimensional Hilbert space. Already spoke about that. Then next, now I call this quantum hidden layers. It's not really quantum hidden layer, but it's a good analogy because neural network have hidden layers. But this is parameterized quantum gates. So, and you'll see in the application. Application is very interesting, the part that we're going to come in. All right. Here, what we'll apply is depending, again, this is just a general representation, but depending on our design, we'll take the state that we encoded and apply unitary operations depending on the design. All right. We'll, layer typical structure will be, R of Y rotation, entanglement gates. Here, the objective is to learn complex feature transformation using, superposition entanglement. I explained that in the beginning of the lecture. These are the two. There are many concepts in quantum, but these are the main ones that you need to be aware of right now. And then last but not least, after you've done this, you need to measure, because what's the point of doing all of this if you're not going to measure? And your measurement here would represent Y, which is your answer. And then you take that answer and compare it to the target, and then you update the the optimization function, you update the theta star, right? Okay. So this is how it looks like. And you see the first one here, this is just a general representation, 4 qubits, right? You can see it, 1, 2, 3, 4. The input encoding is a rotation of X, right? And after the encoding, you apply Ry, theta, and then you apply entanglement layers. Now, got it, that's so far away. All right, okay, please work. Okay, I want you to see the first 4 box with these circle entanglement, that represent 1 layer. And then you move, that represent a second layer. So you can see the Ry of theta entanglement. So this is when I say hidden quantum layer, that's what I mean. And then afterward, you measure. All right? So again, let's compare, all right? So in the classical, I should remove that word. In the original neural network, you have the input layer. Here, you have the data encoding circuit. In the neural network, you have hidden layers. Here, you have rotation and entanglement. And in the neural network, the normal one, you have weights. Here, you have parameterized quantum gates. There, you have activation function. Here, you have entanglement and quantum inferences. And then the other one, you have output layer. Here, you have measurement. Okay? Okay. All right, so back to original.